was a ripple question of where the ripple might be. So I'm using Falsat in order to get it simulated. So if I remember correctly, our there was a ripple question right here, and we were comparing the formulas for what the final calculation was supposed to be. So I was trying to find the calculation. Can you see that PowerPoint pop up? Hello?
No, we're only seeing what you got.
We
It's the
only
false
see
stat.
we only see a circuit law.
All right, hold on. You see that PowerPoint?
Yeah,
Okay.
yeah.
All right, so the last question was trying to resolve the calculation. So this was our final calculation we went with, right? 30 volts and 12 volts, right? For the breakdown on this circuit. Right.
Right.
So I'm trying to verify what the calculations were for the circuit. So I went and built the circuit to see what the simulation would provide as far as data, plus try to see the ripple. All right, so at this point right here, that's approximately where the ripple should be seen, right? The only question that I was trying to come up with is, when is this circuit actually working, right? Now I've changed the voltage, set it 110 is what the test question is, plus I played around with the frequency a little bit. And I've tried to make sure that the transformer was set at the right ratio, and all my diodes are your basic diode, 0.7, and then the same with the Zener at 12 volts. Now the only thing that I found that was a complication is the circuit doesn't want to reach up to the voltage that it should be at. And I know I have my capacitor set correctly, but it's increasing to like the 30 volt range, just doesn't happen. So I changed this to 10, from 10K down to 1K, just to see what would happen. Let me reset the circuit. And I get this slow increase, right? So I can increase the circuit simulation to see how fast it's going to take to get up to 30 volts. It actually takes a while. It takes about 3 minutes before this circuit actually gets up the voltage. So my real question is, what frequency should I be running this at? And I don't believe that should matter, right, Mr. Fan?
Yeah.
So I don't know if this is a software issue versus.
What assignment is this?
This was the quiz.
Oh, the quiz.
Yeah, so there was a question at this point right here, or there was actually just a topic of question whether or not right here at this point of the circuit there's a ripple, right? So when you see the blue, this right here, this is reflecting a ripple, right? So I'll slow it down. Well, actually, you can see the ripple better at 10K frequency, but it's what I'm getting at is it takes a while before this circuit even gets up to 30 volts. And it does, it increases it gets up there. So my question is, Mr. Fran, what would be a cause factor other than the software?
No, I don't think so.
There shouldn't be anything, right? So I even increased the simulation speed just to try and get it up there. And the circuit should be working at its max voltage right away, shouldn't it?
That depends on the capacitor.
So
No.
my capacitor, I have it set at the
1,000.
the spec that it should be. Well, either way, I was just wanting to try and show, or at least demonstrate, what I was doing with the circuit to try and verify some of the information
Yeah.
that
If
we
you
were.
get the value of the capacitor, then the ripple will be smaller or bigger. On the left, on the assignment I just sent out, so you can exercise on that. One, I set the small value of the capacitor and the other one bigger, so you can see how ripple can be affected.
Yeah, so the turquoise, that's apparently the ripple location that you were talking about. But then I was trying to compare this location of the node to this location of the node, and there shouldn't be any change in the there shouldn't be a change in the ripple, right? Because if based on this software, if I highlight this node versus this node, there's a slight peak difference. Let me make sure that the settings are the same.
What program is this?
It's called Falstad. The milliseconds time is
What's the amplitude of your signal source? Is that RMS or peak?
Let's see here. So RMS right now is 84. Anyways, I was just the voltage gets up into range, and I believe one gentleman had like 15 volts. I mean, the diode's working as far as the circuit, but then I believe one of our final answers was 30 volts, so it was half of this. And
Okay.
that's what it reflects here.
Okay, so
All right, so I'll stop sharing.
okay. So today we start with the new one. Okay, we're talking about the transistor, bipolar transistor. Okay, and what we need is when you see the symbol, first thing you're able to recognize what is it, what that device. They are diode, or they are Zener diode, or they are transistor, okay, or JFET or op amp. You must be recognize that. So today we deal with the transistor, and the transistor, you can see this is the one, okay, you get the base and the collector, okay, and the emitter. And this what we call an NPN transistor. Okay, you understand, you get a diode, okay, PN junction. And we'll see they just using diode to make the transistor. Right now, what I want you, when you're looking into the symbol recognize NPN and the PNP, okay, the difference will be the arrow right here, okay, they're going out, NPN, and the arrow in here, they're going in, that will be PNP. Okay, and also another thing for the current, IB means the current of the base, IC current of the collector, IE current emitter. So for NPN, the IB going in, IC coming in, and IE will be leaving. They will be opposite in the PNP. Okay, PNP emitter current go in, and IB the base coming out, and IC collector current coming out. That's what you need to recognize. And also field formula, not much. Okay, normally IE equal IC plus IB. Easy to recognize. Okay, one going in, one going in. And that will be IE equal IC plus IB. And the formula will be applied for both NPN and PNP. And sometimes they say IC, IE almost equal. The reason is the current IB is too small. Okay, and on this formula here, the beta equal ratio between IC and IB. What is the beta?
Current multiplier.
That means current gain. Okay, if beta equal 50, then IC equal 50 times of IB. If you get a 1 milliampere coming in, and the current IC coming out will be 50 times 50 milliamp. So that's why current gain, okay? They amplify the current. Now, this is just giving you a little picture on the physical. You can see this is the NPN right here, N here, N here, okay? Okay, and the P. So NPN, and that will be, this side will be PNP, okay? And that PNP, okay? So when another section of P or N type material is added to a PN diode junction, a 3-section device contains a 2 junction, okay? Now we'll see, you can see that one more easier. So you can see inside that transistor. This is the base, collector, emitter. Basically, you get only two diodes. Okay, two diodes, they can make it up the transistor. This is a NPN, so the diode will be go this way, okay? And this is a PNP, so the diode will be going down here and this going up, okay? So they must be using, try to understand this thing, okay? In order to analyze more later. So NPN will be from, you get a diode from base to collector and a diode from base to emitter. Okay, most of the time they deal with the NPN. Okay, PNP just the opposite with the NPN. And also they given you the picture here. Okay, how that transistor look like, which one will be emitter here. Okay, pin 2 will be the base and pin 3 will be the collector. So when you're doing on the left, you recognize which pin will be emitter, collector, or the base. And this also, if you want to test your transistor, then you can use the meter and how to set your meter and the measure whatever you get. Okay, that means they're working. Basically, they just take a diode, right? From B to E, you get a one diode, and also from the E to B, you can get revert that, okay? And also they show up here. You can look into that, okay? If you want to check it, you can follow it.
Mr. Pham,
Yeah,
why is it when it's in reverse bias, we get 2.6? Shouldn't that be 0?
revert bias.
Right. It shows that when it's forward bias, it's 0.7,
Yeah,
which is, we understand. But when it's reverse bias, shouldn't that be 0?
no, you can try
Okay.
with the good transistor.
Uh-huh.
I never try. That's from the textbook.
Okay, I'll try.
Yeah, try it, and you can see anything. Let me know.
Okay,
Yeah.
thank
You can see this is a circuitry. Okay, I'm talking about NPN. So basically, at this point here, base, emitter, collector. So you can see the current go into the base. That will be IB. Okay. The current leaving the emitter IE. Current going to the collector will be IC. Okay. And basically, you can see two diodes. Okay. However, they draw only one diode. If you're looking back here, okay, so we get a base right here. You get a one diode here. Collector. Another diode here. Emitter. Okay. So now normally they're using the silicon diode. So my question is the voltage from the base to the emitter, how many volt?
0.7.
Plus here, minus here, they will be 0.7
0.7.
volt. Okay, and normally they call that will be VB to E, right? That means the voltage from the base to the emitter equal 0.7. Okay. That only this one only thing I can just remind you to make sure you know. The voltage from the base to the emitter will be 0.7 if the diode on. If they off, they will be open. And also on the other side here, they're just telling you the power supply apply here, negative here, and also the current flow. Emitter coming in, IB leaving, IC leaving. Now, so for this NPN here, okay, if they want to calculate the current IB, that means the current flow here. Okay, I show you how to draw the loop. You suppose the current will be going this way. That the current will be IB, right?
Yes.
Then we can write on the voltage adding up, they're supposed to be 0. So now if the current go, the first thing go to negative, this is the positive. So when they go to the negative, you can say minus VBB. Okay, so when they go through the RB, it's a positive here. That will be a negative here. So they hit into the positive. You will be adding. The voltage here will be what voltage?
IBRB.
V. Talking V first. That will be V of R. Right?
Mm-hmm.
Okay. Then they hit into positive of the VBE. So you adding. Okay, VBE. Everything will be 0. Okay. And now you can see VRB equal IB times RB. So we want to keep that. So IB times RB equal this one you move to the other side. They can be VBB. Move that guy out to the other side will be minus VBA. Now if you want to calculate the IB only, then you can see VBB minus VBE divide RB. So that's why they already gave it to you right here. If you want to calculate the IB, okay, then you take VBB minus VBE, and this VBE equal 0.7. Then divide to RB, you get IB. Okay, so after you get the IB here, you want to calculate the IC. We get the formula IC equal beta times IB. If you get IB, you're able to get the IC. And also, if you want to calculate the IE, I using this formula. I equal IB time 1 plus beta. You already know the formula. IE, IC plus IB. The reason is the IB is too small, so we don't want this formula. Okay? We're using this formula to calculate the IB. Okay, that's what we're talking about. How do we calculate the IB, IC, IA? Any question?
Mr. Pham?
Yeah.
Could you please repeat why VBB is minus?
What I'm saying here, in this formula here, right?
Yes, sir.
Okay, I say you draw the loop voltage, okay?
What?
Current go. I draw this way. Why I draw this way? The thing is this here, current coming from here, right?
Yes.
Okay, so when the current hit into the negative, you get negative. That's why I get minus VBB.
Okay.
You see that? They hit negative before they hit to positive.
Okay. Okay. Thank you.
You
When
can move everything to the other side of the equation
Yeah.
and have reverse the signs.
okay, when you hit to right little here, current coming in have to be positive, leaving negative. So that's why I plot VRB. Then the current go through the VBE here, positive on this side, negative on this side. So that's why I plot VBE. On the voltage added up, they have to be equal to 0. Okay? So basically, you would go to the college university, then you must be doing that thing. Okay? In here, we technician, we just know in general. We don't have to go detailed to do calculation. Okay, so any question regarding into calculation for IB, IC, IE? If it's not, now I'm talking a little more here. Okay, now that is the VB. Right here, VE. And in here, VC. Okay, when we set I want VB, can you tell me what VB equal? From this problem here, what VB equal?
0.7.
Exactly. Now, when I set measure number 1 VB, that means you will be measure VB at the base to the round. Okay, that means you have to measure from here to the round. Okay, VB number 2, VE number 3, VC. That will be telling you they will be connected high side of the meter to B and low side will be to the round. Same thing. If I want to measure VE, then high side of the meter connect to at meter and the low side will be connect to round. Same thing. VC will be connect from collector and the other side will be round. Okay, that will be respect to round. Okay, and now if I want to measure VBE, how do we connect the meter?
High B
High.
is low V.
High will be B, low will be E,
E.
not round. Same thing. I want VCE.
High C, low E.
Exactly. High side, that means from here to here. Okay? Not to round. Only thing this one, they ground it. That doesn't matter. So if I want to measure VRC, how?
High side to VCC, low side to C.
How do we measure the voltage across RC? That means you will measure from here to here, right? That will be VRC. So the high side connect here and the low side connect here across it. Okay? Same thing. If I say, okay, I want to measure VRB, that means you measure across resistance, VRB. Okay? One side go to one side of the RB and the other one go to the other side. That means you measure voltage across it. Okay, so any question? If you have to doing a measurement, a VA, a VB, VE, VC, okay, or VRB or VRC. Okay. Anything, just stop me, okay? Try to make sure you understand, okay? Now, also by conventional, they say, okay, voltage or current, U capital. Letter. For example, VB, okay, or IB. You see, all the capital. VC, IC, same thing, okay? However, for the AC, is lowercase. Okay, VB, IB, VC, IC. Okay, let's try to separate between the DC signal and the AC signal.
Hey, Mr. Pham, sometimes don't they use both for AC? They make both letters small as well?
That's okay. But most of the textbook they using, the way I show you.
Okay,
You can using both, and you know, VB, right?
right.
That's okay. Try to separate between the AC and the DC. Okay, now can you try this one for me quickly? Give me the answer. I just want the answer, okay? Okay, termini B, I, C, I, E, V, B, A, V, B, V, E, V, C, V, C, E. In the circuit show, transistor has the beta 150. I don't know how on notepad they display beta, cannot display beta. Try to see what we just done, okay? To see if we can get it. I can tell you, you can using IB, the formula we just give it to you. Okay, VBB minus 0.75.
Okay.
Happy.
0.43 milliamps.
The first one will be 0.7,
Right,
right?
right.
The next one will be 0.43.
Or 3.
4-3.
I see.
150 times IB.
64.5.
64.5. IE.
Beta plus 1 times IB.
93.
64.
I again, make sure you record this formula. IA equal 1
Plus beta.
plus beta times IB. Or if you want IB, you can using formula 1 divide
Beta.
IE, sorry, IE. Divide 1 plus beta. That's not your formula very good to doing a calculation. Okay, let's see. VB, what the VB you get?
0.7.
0.7.
Perfect. What VE you get?
0.
You don't know, you quit. 0. And now, in order to calculate the VC, I given you the formula. Okay, VC. VCC minus IC.
That's RC times IC.
IC. They don't have a much formula, okay? But they're using all the time, try to memorize. So VC I doing, I get 3.55. Did I get it or not?
Yes.
And the last one will be VCE. VCE will be equal to VC minus E. Okay, so
3.55.
I get 355, right? VC, VE is 0. Okay. Just make it clear for this calculation. Anything confusing, bring it up. The reason I given though the answer the thing is you need to do it over. You make sure you know how to do. Okay, now see what next. Okay, this one they telling you the operation of the transistor, no matter NP, NP, NP. Okay. The first one they say cut off mode. Okay, using for switching application. You can turn on, turn off. Okay. The next region will be called active. If you're using active, that means you want to design for amplifier. And what saturation? When the transistor saturated, they're using for the switching application, like they build the logic circuitry. If you're learning a texture, you're learning you get and get or get, then get inverter inside the transistor inside. However, transistor must be working in saturation. Okay, last thing is breakdown, they will be destroy your transistor. Okay, now cut off diode from the base to the emitter will be off. You already know you get the transistor here. This is the base. This is the collector emitter. And in here you get one diode. In here you get another diode. Okay. So if you get a 0 volt at the base, that means You don't have an applied voltage base, and this diode here will be open. Okay. That will be telling you no current will be flowing. IB, IC, IE, they cannot flow in the open circuit. Okay. For active, that means you want to be active. Then the diode from the base to the emitter must be on, and the diode from the base to the collector must be off, reverted. Okay. Last one, if there is saturation, then both diodes here must be on, and the voltage from C to E. That means they go VCE almost equal 0. Okay, if you're reading here, they already explained to you. So now, cut off means the diode from the base to the emitter off, so no current flow. Open inside the transistor. Okay, and if you want to design for the amplifier, then the diode from the B to E must be on, and the diode from the B to C must be off. And if you want to build the logic circuitry, they must be saturated. Then both diodes must be on. Okay. Now, reading this thing, try to see how much you can understand. For transistor in this circuitry here, what is VCE when V in 0? If you get a 0 input here, they're asking you what VCE. That will be C right here. That will be E right here. And the voltage
The same as VCC.
C to E, they call a VCE. Okay, try to understand, try to read. Tell me what voltage from the collector to the emitter equal if the input equals 0.
VCC.
Okay, now
10 volt.
you can see that will be VCC, that will be RC, and that will be open. And this will be VC right here. When they open, the current IC equal what?
0.
IC equal 0. So the voltage drop across this guy here, IC will be VRC equal 0. Right? The thing is VRC equal IC time RC. And IC equal 0. So VRC equal 0. So if you get a 10 volt here, they drop nothing at the resistor RC, so the VCE must be equal VCC. So that's why when I say when V equal 0, transistor is off. Okay? And VCE will be equal VCC and equal 10 volt. And what the minimum value of IB is required to saturate this transistor with a beta equal 200. Okay. I given the answer here for you. We'll try read it. Since transistor is saturated, that will be telling you VCQE equals 0. Okay. Then the IC saturation equal VCC divided QRC. 10 volt divided 1K, you get 10 milliamp. Can you follow that? When they said transistor saturate, so VCE equals 0. That means they connect directly to the route. Okay? So if you want to calculate the IC saturation, then you can take 10 volt divide QRC. The thing is that will be routed. Okay? So that's why you get 10 milliamp. That will be an IC saturation. The thing is you said that transistor already saturated. They say set therefore IB equal IC divided to beta. 10 milliamp divide beta 200. So you get 50 microamp. Okay. That means the minimum value for the current IB to make it saturated. And they want to calculate the maximum value RB when V in equal 5. Okay, when the transistor is on voltage across RB will be VRB equal V in minus VBE. VBE 0.7, V in 5. 5 minus 0.7, you get 4.3 volt DC. Then now you can calculate the RB. RB equal VRB divide IB. 4.3, that's what here. Divide 50 microamp here. You get 86 KO. Okay? Therefore, just for your guy to read it. Whoever understand it, that's best for you. Okay? Otherwise, we are a technician. We're not dealing with this kind of problem. Now, this is what they call a let's see, graph of IC versus VCE. Okay. You can see this will be stand for VCE. Okay, in volt. This side going up here stand for IC in milliamp. Okay, basically they can display three things. First thing, the area here. They call a saturation region. Okay, the one basically in the middle here. Okay, now here, they will be cut off. And anything in here, they call a active. Okay, now, if I get the point in here, can you tell me this point what the current IC you get? This stands for IC, okay? So you go to the left, and this point here, 8.23, that's okay. Milliamp, that you can get the IC. You want to get the VCE going down. VCE equals 6 volt. Okay? That means you can get any point on the graph in here, and later on you can see they can draw the line. They go a load line. Okay? That if you get a current IC, you get a VCE, that one you can come up with the current IB. Then you can select the resistor to build your circuitry, okay, to get that current and VCE. Now, that's what they call a kill point. Okay, kill point when the engineer they try to design the amplifier circuitry with the transistor. Then they need the load line. They want the Q have to be here. Okay? In the middle here. Why? They don't want to pick the Q right here. You know why?
They want to be in the active region.
Close to saturation.
No. The
He
reason
wants cushioning.
they don't want to pick the point at this point to get the current IC and VCE. Why? The thing is, when the temperature raises, so that point will be moving a little. You don't want it to move to the saturation. Saturation, that means not amplifier. They cannot amplify anything. You see that? Or they don't want to select the point right here. Temperature changing, they can move to the cutoff. So they can not working like the amplifier.
They want fixed points.
Yeah, normally they pick in the here, in the middle here. They can move up or move in little down. They still okay. Okay? They still be amplifier. But therefore engineering, when they design the circuitry, okay, we only think, make sure you understand. And now, let's see, what else? Okay, did bipolar transistor a current control divider? Okay? Bipolar transistor, they call current controller device. Why? Why they call a current controller device? Why they call a current controller device? Who knows?
In horizontal region with different VCE, we have only one IC, almost IC not changing too much, but changing a lot of VCE.
No, that's not a current controller.
The base is, right?
No, come on. How come we say this is a current controller device? Okay, I can tell you. Current IB coming in. Collector will be coming out at the collector. So basically, if the IB equal 1 milliamp, beta equal 100 and IC equal 100 milliamp. That will be telling you if you change the current IB, you change the current IC. So that's why they say a current controller. Okay? You change the current and the output will be changing. If you want the output IC, you have to know IB. If you change IB, then you change IC. They really controlled by the current IB. That's why they call a current controller.
Or a switch.
Who cares? But what I'm talking in general here, if you change the IB, then you will be change the IC. And IC basically depend on IB. Okay? So that's why IB will be controlled that device. That's why they call a current controller. The thing is when you're learning a JFET fusion transistor, you changing the voltage, that means the output changing. So they will be a voltage controller, not current. So now can you understand what that means for current controller?
Yeah.
Okay,
Just for the-
telling
For
how
anyone who doesn't know what a JFET is, it's a junction field effect transistor, and I'm sure
Right.
we'll learn about it in detail later on.
that will be learning later. Fusion effect transistor, okay? JFET, MOSFET. But transistor will be current controller device. Make sure you must be memorize that. And now the thing is that depend on, you can see that depend on IB. This for the current IB. IB. So you change IB, you change the current IC. Okay? So this will be telling you how to draw the load line. In order to draw the line, you need 2 points. 1 point A and 1 point B, and you draw the line that will be Q, that will be Q when they intersect with the current IB. Okay? And you can see right here, point A at saturation, and you can see they equal 10 milliamp. So that will be point 10 milliamp here, and point B will be cut off. You can get VCC right here. So if you draw that one here, okay, then point B here, what the voltage point B here?
0.
What VCE? What the voltage here? You understand
VCC,
that one here?
VCE is zero,
VCC.
approximately zero.
Right here.
No, voltage is VCC. Okay, 10 volt.
Oh, yeah.
Okay. Then the point in here, you take 10 divided to 1. They will be 10 milli. You get 2 points. Draw the line. That means DC load line. You go college and you go university. You must be doing it. Now, you can see they show you here how cut off. You see, cut off means no current flow. IB, IC, IE equal 0. So they like the switch. Okay, they can close it, they can open it. Okay, like they say, open switch right here. Saturation. Okay, that means like the switch, same thing. Okay, using for logic circuitry. Okay, so they get a 3-mode operation: amplify, saturate, and cut off. Okay, so this problem we already done. Okay, you can try. Okay, exercise. We don't want to spend time keep doing the same thing. Now, admitter bias. For this circuitry here, they want to calculate the IE. Okay, and I already calculate for you right here. VE means right here. VE. Right here will be VC. Right here will be VB. Okay, they say VE, that means the voltage from here to the round. You understand the voltage here. What voltage?
0.7.
Make sure remember 0.7 and point here, negative here. Okay, so they calculate the VE first. Okay, right here. Then IE, you take VE divide to RE. You get 1.95 milliamp. And same thing, VC equal VCC minus IC times RC. We just done it. Okay, and VC equal 13.05 and VCE equal VC minus VE. That's another way try to doing a calculation. However, you understand, you know how to do B-SPI or MSIM7 simulation. Who cares? You can just run simulated, you can get whatever you need. Okay? Computer can do it for you. Now, another way, admitter feedback bias. That's what they're talking about. General DC bias. What that mean? That means the transistor, they only working if they get a power supply. That's for DC.
New line.
With them, without the power supply, transistor not working. They need the power supply. One or two power supply, that doesn't matter. That's what they call a DC bias. How do we make a transistor with the power supply? They get a too many ways to bias. However, we only emphasize on the one normally used. Okay. This one they say admitter feedback bias. That means they need only 1 voltage VCC. Okay. And 1 RB. They still working. They say better than Bay bias. That means better than what we just done. Q point still move and not popular. They not using much. Next one, Bay bias. That means they connect this way. They call Bay bias. The least predictable. Q point move with the replacement. Q point move with temperature. Not practical. If you want to how to do calculation, go run simulation, then you can get any value you want. But this is not normally be using. Okay, be using. The thing is they get too much problem. So that's why they say not practical. The next one, collector feedback bias. That means the bay go to the RB, connect to the collector. Better than admitter feedback. Okay. Q point still moving. Limited application. So that's why. Normally you're working on a company. You see the circuitry they design. You not see this kind of circuit. Okay. Not good. Two power supply at meter bias. Now they're using a one power supply positive and another power supply negative. They require two power supply. They very stable, but they not being yield. Why? They want one power supply only. Two power supply need more room and have to pay more. So that's why. Two supply steep at meter bias. Okay. So that's why they're using two here. I already given to you how do we calculate it. Okay. Now this one, the one will be emphasized using all the time. For this one, they adding R1, R2, and they using only one power supply. So if you want the voltage at the base here, you're using the voltage divider. You take VCC times R2 divide R1 plus R2. That's what I given to you right here. So they just using only two resistors substitute for another power supply. Resistor less than 25 cents. Okay? Power supply, maybe you have to pay more, really more. Okay? However, company make the circuit board, they not make only one. They make a 50,000, 100,000. That means too many board. Okay? So the cost, that's a problem. Okay, now, if I want to calculate the VBB here, I using voltage divider. VCC times R2 divide R1 plus R2. Then if I want to calculate the VE, you understand it right here, plus minus 0.7. So that's why you want to calculate the VE, you take VBB minus 0.7. Okay? And after you get the VE, if you want to calculate the IE, very easy. IE, VE, IE. You see that? Yeah. Okay? After you get IE, you can calculate the IB by this formula. IB equal IE divide beta plus 1. And after you get IB, you're able to calculate the IC, beta times IB. Okay? If you want to calculate the voltage VRC right here, they will be equal IC times RC. Okay? And if you want VC, then we already show you VCC minus IC times RC. Okay? Now, if I want VCE equal what?
VC minus VE.
I want VCE. That equal what formula?
VC minus VE.
Exactly. VC minus VE. You already know VC. You already know VE. Take the difference, that's why you're able to get the VCE. Voltage from collector to the head meter. These are circuitry, very, very important, okay? Any question on those calculations? No, here, okay? However, we run out of time. You have to take the quiz. then this one you try to do your calculation, okay? And next week will be telling you on of the calculation and the formula we already given to you here, okay? And next one will be PNP, okay? That one, okay? PNP, and okay? And now then we done for the DC buyer. And the next week we start with the amplifier. Okay, so now we'll try to do the quiz. I try stop this guy. Okay, that take about 15 minutes or 18 minutes. So you guys can be okay. Let's see. Quiz, bipolar. Okay, we'll share that. Oh man, it's the wrong one. Is it you done on this?
Yes, done.
Okay, the thing I saw some wrong with the
Number one, right?
something wrong with the timer. I don't understand why they still wrong with the timer for sub. I have to check that. Pin number 567. You don't need any more textbook, only try to go through the handout. Make sure you can understand anything in there. Okay. Now I can go to let you guys know what the answer. Okay. So the first one, we already know how to do it. And you get the 0.059 milliamp and 5.3 milliamp. Okay. And they want IE. IE equal IB times 1 plus beta. You get 5.37 milliamp. And if you want to calculate the VC, then will be VCC minus IC times RC. Okay. And 7.83.
I'm getting different answers.
Me too. I think the first one, the IE, I think that was wrong.
Which one?
IE, I get 21.84 milliamp.
You want talking about what number?
Number one.
Number one, VBB
Oh, no.
minus VBE
Number,
by
Hang
RB.
on. Number one, I get 0.24 milliamp.
Yes, like me.
yeah, it's 0.24 milliamps. is
Yes,
correct.
0.241.
Let's see, I try to calculation again. Okay, VBB 6 volt and minus 0.7, you get 5.3, right?
Yes.
5.3 divide to 20K, 22K. Okay, 0.240. I do it
Yes.
wrong. 0.241.
Yeah.
Okay, and this one we multiply by 90. So 21.68.
Yes.
21.7, yes.
Okay, correct that for me. Okay, too much things I do it, I doing calculation wrong. Okay, now that one will be wrong, right?
Mhm.
Yeah, so
I
the
equal,
21.9.
you say 21.9,
Yes.
Yes. Agreed.
I can get 21.9. How about VC?
4.23.
4.23.
Agreed.
4 point what?
23.
23. Okay,
Okay,
yeah, thank you.
welcome.
For operation net amplifier, The bay of the NPN transistor must be positive with respect to the
Emitter.
Yes, A.
That means the diode have to be on, right?
Yes.
We have
Yes.
to be on. Number 6, the emitter current is always ABCD. They will
D.
be
Yes.
D as in David.
D. Yes, agreed.
yeah, the thing is answer. A means emitter current must be greater than B. And also, they must be greater than collector. So the answer will be D. The beta of the transistor is what?
Right.
A
Current
as in
gate.
Adam.
Like I just talked to you. Current gate. The approximate voltage across the forward bias bay emitter junction.
B.
B, right?
Yes.
0.7 for silicon. 0.3 for germanium. Number 9, when operate in cutoff and saturation.
B.
Transistor apply B with
Ano, good night.
10 in saturation. VCE, ABCD, and
Minimum.
Minimum C.
minimum. They close to 0. Okay. For this calculation here, I already given you the formula. If you want, calculate IB. VB minus VBE divided by RB. If you get a different one, let me know.
Looks good.
The good one, right?
Yes.
You
Okay.
get A, Mr. Pham.
Now, yet, even you already get a simulation for DC bias. Also, I given you the common emitter amplifier, common collector amplifier. You still know how to do your simulation. Think of when you do a simulation, you don't care about the circuitry. If you know how to simulate, do the right way, then you get the right answer. The thing you don't never expect when you're working in a company, you're able to understand the circuitry inside. No way. Okay? Only thing if you know right thing to do, how to using your oscilloscope or the meter, then you can get the right answer if they work it. Even I engineer, sometimes I still cannot understand completely what the circuitry. Take a long time.
So if you have a problem, you call Sam, right?
No, you call Mrs. Smith.
Got you on that one, Sam.
No,
Thank you.
next week.
Okay,
Okay,
Mr.
see you
Pham,
next
thank
week.
you.
See you. Goodbye.
Tomorrow.
Thank you.
No,
Thank you.
welcome.
Thank you.